Hello friends, I welcome you in lecture number 15 on higher order partial differential equations. In previous lecture, we have discussed general method of finding particular integral of non-homogeneous PDE with constant coefficients, and we have seen that in that method we have one restriction, that this function of d and d dash must be homogeneous, and we had developed one formula for this method, that we recall that if we want to operate this type of linear factor on the function fxy on the right hand side, then we will replace this y by c minus mx and we will integrate with respect to x. Y is to be replaced by c minus mx, so that this function becomes function of x only, and then we integrate this function with respect to x, and after integration we will replace c by y plus mx. This we have to remember for this general method. Suppose we are having more than one factors, linear factors in FDD dash, then we will start from right hand side and we will operate each of these linear factors on the right hand side using this formula. So with this in mind, we try to solve this non-homogeneous partial differential equation. First we are writing it in the form of d and d dash. Here I have del square z by del x square, that is d square, minus del square z del x del y, that is d dash, minus 2 del square z del y square, that is d dash square, z equal to y minus 1 times e to the power x. And here we can observe that f d dash is a homogeneous function in d and d dash. So first we have to solve the corresponding homogeneous equation. Given equation is having non-zero function on the right hand side, so it is non-homogeneous, and to solve this non-homogeneous equation we are first solving the corresponding homogeneous partial differential equation. So that we can write by considering right hand side equal to 0. So my homogeneous equation is this one, and here fdd dash is homogeneous in d and d dash. So as we know, we have to replace d by m, d dash by 1 in this function and equate it to 0. That will be the auxiliary equation. The auxiliary equation is m square, d is replaced by m, minus m into 1 minus 2 into 1 equal to 0. Therefore this we can solve easily. We replace this minus m by minus 2m plus m, and we try to factorize. Here we can take m common, so we have m minus 2. This we can rewrite as 1 into bracket m minus 2 equal to 0. Again we take m minus 2 common, and we have m minus 2 times m plus 1 equal to 0. This gives me two different values of m, 2 and minus 1. And corresponding to the value of m, the part of complementary function is written as some arbitrary function of y plus mx. So we write two functions corresponding to each value of m. For m equal to 2, we will write arbitrary function of y plus 2x, say phi 1. For m equal to minus 1, we write arbitrary function of y minus x denoted by phi 2. So this is complementary function, and here fdd dash is homogeneous in d and d dash, and it is d square minus d dash, d square minus d dash minus 2 d dash square. And we have seen that we obtained two values of m, 2 and minus 1. So we write this as a product of two linear factors of the form d minus m d dash. So first we take m equal to 2 and we have d minus 2 d dash, and for m equal to minus 1, if we take m equal to minus 1, here we have d plus d dash. So I have written this fd d dash as a product of two linear factors of this form, d minus m d dash. First m equal to 2 and then m equal to minus 1. Now we try to find out particular solution or particular integral. So particular integral is 1 over fd d dash operated on the right hand side, which is y minus 1 times e raised to x here. And now we replace this fd d dash by this product of these two linear factors, d minus 2 d dash times d plus d dash operated on function y minus 1 times e raised to x. Now we have to apply that formula. We know that 1 over d minus m d dash fxy, this is equal to integral of fxy by replacing y by c minus mx integral with respect to x. So we replace y by c minus mx, and after integral we will replace c by y plus mx. So first we operate this factor d plus d dash. We keep this as it is, d minus 2 d dash as it is, and here if you compare with this, you will see that m is minus 1 here. So if m is minus 1, y is going to be c minus minus 1 into x, that is c plus x. So here I will replace y by c plus x, and after replacing y by c plus x, I will integrate with respect to x. So here we write that y equal to c minus mx, m is minus 1 here, so that is y equal to c plus x. Now we have to integrate this with respect to x, and we can see that there is a product of two functions of x, and for that we will apply integration by parts. So we consider u equal to c plus x minus 1, v equal to e raised to x. So first we keep u as it is, that is c plus x minus 1 as it is. Integral of e raised to x is e raised to x minus derivative of this function with respect to x, which is 1, into integral of this function with respect to x, that is e raised to x. In the next step I have to write derivative of this function 1, but that becomes 0, so here we stop. And here we keep in mind that we have used the fact that y is c plus x. So now let me simplify all these terms. Here I can take e raised to x common, and here I will be left with c plus x minus 1, and there is 1 minus 1 here, e raised to x common, and here I am writing that from this I can write c equal to y minus x. Now we have to replace value of c in the form of y after integration. Now we have done this step. We have replaced y by c plus x using that formula, and this is the integral. Now after integration, don't forget to replace c by y plus mx. Here m is minus 1, so we have c equal to y minus x. So now I am replacing c by y minus x, and there is plus x here, and this is minus 1 minus 1, that is minus 2 times e raised to x. So now in this step c is y minus x. This is very important step. Don't forget to replace c by y minus x after integration. Now let me simplify the bracket. here x will get cancelled and we have y minus 2 times e raised to x. Now again we apply that formula. We have to replace this y by c minus mx, and if I compare this with d minus m d dash, we have m equal to 2. That is, I have to replace y by c minus 2x here, and then I have to integrate with respect to x. So now I am replacing y by c minus 2x, and there is minus 2 here, and into e raised to x dx, where y is replaced by c minus mx, m is 2, so we have c minus 2x. Now again we integrate with respect to x using integration by parts. This is as it is, integral of e raised to x is e raised to x minus integral of this bracket with respect to x is minus 2 into integral of e raised to x is e raised to x. And here we keep in mind that from this we have y equal c equal to y plus 2x. Now you can see, I can first simplify this. I take e raised to x common, and here you can see c minus 2x minus 2 and plus 2, that will get cancelled, and here I write c equal to y plus 2x. Now after integral, again I have to replace c by y plus 2x. So if I am replacing c by y plus 2x, 2x will get cancelled, and my particular integral is y times e raised to x. So this is general method. You can apply this method for any function on the right hand side, and all you have to remember is this formula. You have to apply linear factors 1 by 1, and to apply linear factor d minus m d dash, you have to remember that replace y by c minus mx. So first we have operated this factor d plus d dash on the right hand side, and if we compare d plus d dash with d minus m d dash, we find that m is minus 1. So we replace y by c minus mx, m is minus 1, that is we have replaced first y by c plus x, and then after integrating we are replacing this c by y minus x, and again we operate this factor d minus 2 d dash. So for that, here m is 2, so we replace y by c minus 2x in the right hand side, and then we integrate, and after integration we are replacing c by y plus 2x. And finally, don't forget to write down the general solution. Therefore, the general solution is z equal to complementary function plus particular integral, and therefore z equal to complementary function was arbitrary function of y plus 2x plus another arbitrary function of y minus x plus y times e raised to x, where phi 1 and phi 2 are arbitrary functions. So remember this method. This is easy method. If you don't want to apply shortcut method, and if you are comfortable with this method, then you can use this formula for any function on the right hand side. There is no limitation. The only limitation is that our function of d and d dash, that is capital F, must be homogeneous in d and d dash, and we are considering y equal to c minus mx everywhere in the right hand side function, so that our function is converted into function of x only. Then we integrate this function with respect to x. After integration, we have to replace c by y plus mx. So this is all about this session. I hope you like it. Thanks for watching.